Welcome back to educator.com, Intermediate C++. Today we're going to be doing some more work on object-oriented programming, some more things that you need to learn about. Okay, now with all sorts of various ways of overloading, we didn't have time to cover overloading of the constructors much last time, so today we're going to cover a little bit more of that, how we can overload to allow different ways of initializing the new object that you're constructing. So we can have an initialization list is a unique way for a constructor to initialize each of the members in the particular object. And we're going to talk about destruction a little bit. So once you construct something, you always have to destruct it, and which means I need to go get some memory for this object. So, okay, I don't need it anymore. Just give it back. And we'll talk about the class members and parameters. A little bit of discussion of giving them meaningful names. Like if it's the age of the widget, don't call it A, call it age. Three letters of type. It's not a big deal. Functions and classes can also be a friend. We're breaking the object-oriented rules a little bit when we have friends, but sometimes there are occasions where you need to have that in your design. So we'll have friend functions and classes that allow you to write a specific class or specific function that is outside of your class but still has access to the private members. Now you can design your classes to have subclasses. You should not really, in general, just, here's a great class we can derive from that. No, you should take a great class that has been designed to be derived. The methods are designed to be called by somebody that derives from it. You've got protected members, etc., etc. Virtual functions that will be overridden properly. And we're going to talk about separating your classes into compilation units and an interface header so that you can have the code for that object in a compilation unit by itself. You say, okay, here's my compilation unit. You can now compile this with all the other compilation units that are part of your application. And we'll talk a little bit about when not to use object-oriented techniques. I mean, you'll see a lot of stuff out there about how wonderful object-oriented stuff is, and all the different things. Many programs out there that didn't used to be object-oriented or now have got object-oriented ways of handling their particular code, because object-oriented is a good way to do things, but there are occasions when it's overkill. So we'll talk about when it's not appropriate to use object-oriented techniques. So you're going to overload some constructors. So every time you use the same name for a particular function, in this case a constructor, but you have different parameters, you're overloading it, which is a kind of polymorphism. So it's useful to provide other constructors. Now, also notice if you provide any constructor at all, the compiler will not write a default constructor for you. You may need to also have a default constructor. So here we have a default constructor for horse. So the horse class has got a name, it's got a speed, it's got the time it was created, and we'll include the time header so we can get the time t type, and we'll also get the time function. So here we have a default constructor. We're just constructing a horse, just some horse, and rather than having an unnamed horse, we'll just give him an empty string as his name. And since we just constructed him, his speed is 0, and we want to know when this horse was constructed. So we'll say the time created is equal to the current time. Now, we may want to give a name and a speed other than the default. So we'll have an overloaded constructor. We promise not to change this parameter. We're going to give it the name and the speed. So I've got n is going to be the name, s is going to be the speed. So we're going to construct this horse and set the name equal to n, set the speed equal to s, and set the time that is constructed. Now, we're not going to allow the caller to change or set that. This is something that is private. The time it was created is private. Now, we might want to return to the caller, let them know when it was created, but we don't want the caller to be able to change it. And since it's a private member, we don't have to give them access to it, so we won't. But in each constructor, this definition is when this object was created. Every constructor that we have to write will set the time created equal to the current time. Now, there's another syntax which can be convenient for constructors. You'll see this from time to time. It's called an initialization list. You'll have horse, and you'll have A and B and C and whatever else is in there, and then you'll have the beginning of your block, and your member is equal to your parameter rather, and your next member is equal to the next parameter, etc., and that'll all be inside of a block. Well, constructors, there's a little shortcut that you can use called the initialization list, and so we have string n, constant s, and we'll have the colon. This is we're starting our initialization list, and the name will be initialized to the parameter. And then we have comma, and then the speed is initialized to the next parameter, which is s. And of course, our time created is still set equal to null. So this gives us an equivalent way to initialize the members in a particular constructor, but it's a little bit more compact. So occasionally you'll see it done this way, occasionally you'll see it done this way. Don't worry about it; it's pretty much the same thing. Now let's talk about destructors. There can only be one destructor. You don't overload destructors. You don't give parameters to destructors. You just destroy. So you don't call the destructor. When the object is destroyed, the destructor is called automatically. Now the destructor can be called when the instance is deleted. So somewhere you can have horse. Let's have it has to be a pointer. We'll make it a new horse. So you'll allocate memory to a new horse and pass a pointer to it to H, and you use it however you're going to use it. When you don't need it anymore, you say, let's go ahead and write that L right. We delete H. Now the horse's destructor will now be called. All the memory was allocated should be given back to the system. Or that's explicitly or by leaving the scope. Leaving the scope is like you have an open bracket and you declare your horse. You do whatever you're going to do with it, and then you have a closed bracket. This could be like a while loop, it could be an if clause, or you just randomly stick braces inside your code for no particular reason. So when it leaves scope, the objects that were defined inside the scope are destroyed. So the destructor will be called. So memory resources that are allocated in the constructor must be released or destroyed. If you don't provide a destructor, the compiler will give you a destructor. But if you do anything that allocates memory inside your constructor, you need to provide a destructor to explicitly destroy the resources that you allocated and return them back to the system. Now, if you're going to derive the class into other classes, your destructor should be virtual. So this makes certain that the instances of the derived classes, if they're destroyed, the base class destructor will also be destroyed, the superclass destructor. So as an example here, we'll have horse, and we'll write a destructor for it, and we'll derive racehorse. And if we define a racehorse, let's call it R, and let's just put that inside of a scope. Now, if you don't define it as virtual, this destructor may not get called. But if you do define it as virtual, then the racehorse destructor will be called, and then the horse destructor will be called. So the horse could be allocating some memory. The racehorse derived class could be allocating some memory. Both of those memories need to be returned back to the system. So declaring it as virtual makes certain that destroying the instances of subclass will also destroy allocations that were done in the base class or the superclass. Now, it's not necessary if the class is not designed to be derived as a subclass. I know when you run Eclipse and you create a new class, it will automatically set your destructor to be virtual. So as far as I'm concerned, the jury is out whether it's always a good idea to include virtual. I've read some opinions that said if it's never going to be declared as it's never going to be derived to a subclass, and you should not define it as to be virtual. I'm not sure which is the best way. I'm pretty sure that always defining as virtual doesn't hurt, but I think some more research is required in that area. All right, what's in a name? So we have a constructor with parameters. Your member fields should have meaningful names: age, weight, height, etc. Your parameters on your constructor should also have meaningful names: age, weight, height. Now, I've been using examples all over. I've been using the first letter of it. So if it's age, I've been using A for the parameter. If it's for weight, I would use W. That's not a good practice, but for the purpose of the class, I've been taking shortcuts. So how do you tell the field from the parameter? In the example here, we have a class auto. The year is it's a string of model. The short is the year, so that'll be like a 2012 Ford, for example. And here's our constructor. We're using the same names as the parameters. So we're setting model equal to model, year equal to the year. Well, in that specific context, it's pretty obvious which one you're looking at. Obviously, what we're doing is we're setting our member variables equal to the values passed in by our parameters. But there are all sorts of various other algorithms that you could put inside of a constructor where it's no longer that obvious. And what you do in that case is use the this keyword. Some compilers may even flag this as an error, but some compilers will actually figure out what you're doing. But to be absolutely sure, you use the this keyword. The this keyword is a pointer to this instance. And the way you do that is you put this in front of the one that is the member. So this allows you to use the same names as your parameters as you have in your member. And you say, well, why not use M and Y when you have your constructor? Well, the reason why you probably don't want to do that is many IDEs that you would use, in particular Eclipse, which is the one I use all the time, when you start typing out something, like say we start to define this, and I say I'm going to define auto A, and I'm going to give it an initial value. Right away, it'll go look up. Oh, auto, the constructor. These are the different kinds of constructors. The first thing you need to give it is a string. It'll put a little pop-up right above it as you're typing. You need to give it a string, and you need to give it a string called A, or M, because you put M there. You need to give it a string, and it's called M. I say, well, what does M mean? So now you have to stop what you're doing, go look up the definition for an auto. So, oh, the first thing you need is model. But if you do it this way, and don't use the shortcuts here. Your first one is model. Your second one is year. When you get the little hint box that pops up in your Eclipse, it will say your first parameter needs to be model. Oh, yeah, the model of the auto, of course. So then you don't have to look up anything. It's displayed right there. So you just put in there that it's a Ford. And then comma, they'll put up another hint that the next one is supposed to be a short, and it needs to be the variable years. Okay, well, the year of this auto is 2012, so I'll just put 2012 in there. And so that's a very good reason to match the parameter names to your member names, and then use this keyword. Now, I've seen all sorts of crazy things to avoid needing to use the this. Just recently, I saw something where what they would have, instead of short and year, instead of short and y, it puts an underscore in front of it, and then year. So when you have your little hints here, it'll say short underscore year. You're supposed to ignore the underscore, and then what you'd have in here in your code, instead of saying this year, you would just say year as the member is equal to underscore year as the parameter. Personally, I think that's even uglier than using the this keyword. So, but that's up to you. Whatever you want to do. If you want to use underscores for your parameter names, that's fine. If you want to use shortcut letters, I've also seen they would say a year. So in other words, you're giving a year to this particular object, which is not as ugly as the underscore, but still kind of kludgy. But at any rate, the this keyword is there. It's available so that you can distinguish between the members and your parameters. Now, friendship functions. Sometimes an external function has to be designed that requires access to the private and protected members of a specific object. Now, it avoids strict object-oriented principles because there should be no outside object that has direct access to your data members. You're not supposed to do that. C++ says, well, we recognize that there are exceptions to every rule. This is how you handle those exceptions. You define a friend. So you declare the function or class using the friend keyword. So here we have an example. We have a horse. It's got a name, it's got speed, it's got constructors, methods, destructors, what have you. And it has a friend function with no return. It's called rider urges, and you pass it the horse as a parameter. So somewhere in your code, you can define that when the rider is urging on the horse, his speed is changed, is incremented by 1.2. You take the speed, multiply by 1.2, and set it equal to that. So that means the horse runs a little bit faster. So in your code someplace, you can define your horse. Say my horse is H2, and we set his speed to something somewhere else in the code. We say that which would be one of the methods up here. Set the speed equal to 15 miles per hour, and somewhere else in the code you call this function. The rider will urge the horse on a little bit, and we'll pass it the horse that's being urged. And since this is a friend function, this function has got access directly to the speed data, so we can increase the speed just a little bit, because that's what the rider's urging is done. We can also have an entire class as a friend, which involves a little bit peculiar syntax, because now we have a rider class, in this particular example, which is going to be a friend of the horse class. But the rider needs access to the horse class in order to do what it's going to do, which is to urge the horse to be a little bit faster. But this has to be declared first. C++ means you declare everything before you use it. So we pre-declare horse to be a class, so that the rider, so the compiler at this point knows, oh, okay, there's a horse, there's a class somewhere. I'm going to get the definition of this later. So, but it knows that this is okay and it's legal and keeps going. Now here's our horse class, which has got the name, it's got the speed, and it's got the public constructors and methods and destructors. And now we have a friend class rider, which we don't have to define because it's already defined right up here. But now we have an implementation of urge, which comes even later in the code. So the rider urging the horse, just like the function, is increasing the speed by the same amount, multiplied by 1.2. So this is maybe a little bit confusing. We have the horse, and its friend is the rider. And its definition for rider is before the definition of horse, and the definition of horse is a class, just so that it knows it's there, is before the rider. And then the actual implementation of the code is later still. Now, as I mentioned briefly a couple of times, when you're designing your classes, your objects, and your structures, and how you're going to put everything together, if a class is going to be derived, you have to design it that way. It's not a good idea. Sometimes you can do it and get away with it, but if the class was not designed to be derived into other classes, if it was designed to be standalone, it's usually not a good idea to try to derive from that class. So classes that are designed to be derived, you frequently need to use a virtual method. That buys you a few things. So if you see a class and it's got no virtual methods at all, you probably don't want to derive from it. We'll just define a different class, and we'll define it such that it is to be derived into subclasses. So we'll add the virtual keyword to specific public methods that we expect to be overridden in our subclasses. So it allows the subclasses to override the method with a specialty method that works explicitly for the derived class. If you don't do this very often, you'll find there are circumstances where you will try to call the overriding class, and you'll attempt to call the overriding method in the derived class, but instead it will call the superclass method. If you add the virtual keyword to the public method of the superclass, then you'll get the one that's overridden instead of the original one. So if you don't use the virtual, if there isn't any derived method, then it'll go back to use the superclass anyway. I'll do a real quick example here. Let's say we have our vehicle, and we have set speed. It's got speed as a attribute. We'll set speed, and that will be a public method which sets that speed. Let's make it virtual. Now we have auto, which is a vehicle, and we'll override the set speed method. And we'll use a completely different algorithm to set the speed. So when we define auto, and we say auto set speed, we will use the set speed in auto, not the virtual method in the vehicle. Let's have another example. Let's have a ship, and let's not override it. Let's not give a set speed. So now when we define a ship and we call it set speed, it has to use the set speed in the base class or the superclass because it did not override it. So also make sure you add virtual keyword to the destructor so that when the derived class is destroyed, so let's say we say delete ship. We'll delete S. We want to call the ship's destructor, and because we have the virtual on the destructor, we'll also call the vehicle destructor. So you make certain that the base class destructor is also called when any of the derived class constructors or any of the derived class objects are destroyed. The derived class objects destructors will be called, and the superclass destructor, because you specified as virtual, will be destroyed. So basically, virtual is saying, I have a class, I expect other people to derive from this class. I expect them to override this particular method if necessary. I expect them to have their own destructors, and I expect my destructor will also be called because my destructor is virtual. But if you don't override my method, that's fine. You can use my method, but it's set to be virtual, so it can go whichever way your design goes. Now let's talk a little briefly about an abstract class. It's a class that is so much needs to be derived, it can only be derived. So you define this class. This class should never ever be instantiated, but you need to derive other classes from it. And how do you define that? To set it up so the compiler will enforce that for you. You set your pure virtual methods. Let's say we have vehicle. We want vehicle to be an abstract class. There's no such thing as a vehicle. You can't say vehicle V anywhere because we want this to be an abstract class. If you want to make a vehicle needs to be an auto, which is a vehicle, or a boat, which is a vehicle. So we have a internal variable of speed, private, a protected acceleration. We want the vehicle to be able to accelerate. And we have a set speed, which will set the speed of the vehicle object or any of its derived classes. And here we have a virtual void acceleration, give it a rate, and set this method to 0. So the derived classes must override this particular method. And if it doesn't, the compiler will catch it and say, hey, you messed up right there. So here's a class auto, which is going to derive from this vehicle. And we're going to have string make, which would be like Ford or Toyota, what have you. And we'll override that pure virtual method with our own acceleration. We will use the vehicle set speed. That's fine. We can use theirs. But we want to use our own acceleration method, such as if you're hitting the brake or if you're hitting the gas pedal. And you write whatever code goes in there to do the acceleration, to run the accelerate method based on the rate for the derived class auto. So here, this is a abstract class vehicle because we have this virtual void accelerate. This particular method makes the entire, just having one here makes this entire class an abstract class. You cannot do vehicle V because of that in there. The compiler will complain about it. All right, now let's talk about compilation units. Up until this point, our classes have all been defined all together. We've had the implementation, the definition of the methods and variables, and everything else was all up together, all bunched together on that same file, which is great for showing the syntax of how it works. But it's not really usually, that's not the way it's usually done. It's not the best way to do things. So what we typically do, we have our classes and they're divided into an interface portion and the implementation portion. The interface portion will be in an include file. You have an extension like .h or .hpp, HPP because it's a C++ include file. The implementation portion will go into this should be a capital C because the lowercase c means it's a C file, or C+, or CPP, which means it's a C++ file. And you'll need to use namespaces to associate. In your CPP file, you'll define all of the methods that are defined. You'll implement the methods that are defined in your classes. How do you associate them with the correct class? You'll be using the namespace operator, which we'll see in a moment how that's done. The implementation portion You can compile that separately. You've got a CPP, we've got an auto class. And we put it in here, we call it auto.cpp. And we'll compile that into object code. So that'll be auto.o. That's the object code. And then we can link that to all of the other compilation units that are in the application that you're running. So they can be compiled separately. You make some changes to something else. If you don't make any changes to the CPP, you don't need to recompile it. Just reuse the object code. Now, any units that are using your auto class, all they have to do is include the include file, the include.h. That way the interface is defined and the compiler can check the syntax to make sure you're calling the auto object correctly. So here's an example. Now, later in the class, we'll talk about macros. Right now, all you need to know is this is what's called an include guard. And the reason why you need an include guard, it's very possible that you'll have various applications, various compilation units, and they're pulling in various include files. Those include files can be pulling in various other include files. And you don't want this definition to show up in your code more than once. So what this is doing, if this particular variable, this particular macro, is not defined, then we'll proceed until we get to the end if. This is if not defined. Now, what's the first thing we do inside here? We define it. So if somebody else includes, so you have a particular piece of code that includes this, it comes in here, this is not defined. Oh, now it's defined, and here's your definition is placed inside the code. If another piece of code includes it again, we say if not defined, oh, well, it is defined, so this will not be brought in a second time. So this prevents multiple inclusions. But here's our vehicle class. We have a speed, we have a constructor, we have an overloaded constructor that sets the speed when the object is created. We have a destructor, there tilde says it's a destructor. We have something that's get the current speed, and we have a couple of methods for speeding up and for slowing down. And you notice there's no code here. This is just a definition of the interface to the vehicle object. This is your vehicle.h file, which will be included into any particular code that needs to implement to a vehicle object. And also, particularly the vehicle.cpp file, which is right here. Here we're including vehicle.h. And now we need to define all of those vehicle class members, member functions, so that they actually have an implementation, so they'll actually do something. And here we have the namespace operator and the name of the class. Here's our constructor. This is our default constructor. So if a vehicle is constructed without any parameters, we'll initialize the speed to 0. Here's our overloaded. Vehicle owns this namespace, the vehicle constructor, with a parameter, s. And we'll use the initialization list to set the speed to the s parameter, and there's nothing else we need to do except to have the open and close brace because this is a function. Here's our vehicle namespace destructor for the vehicle class, which doesn't need to do anything because our constructors are not allocating any memory. So all we're getting is a compiler allocated speed variable, which you'll automatically get rid of for us, so we don't need to do anything inside the destructor. Here's our method. Our getSpeed method returns a float to get what the current speed is, the vehicle namespace, the getSpeed method, there's no parameters, and we return the current speed to the caller. Here's our speedup method, which is no return value. It's owned by the vehicle class. And here's the rate being passed in. And what we're going to do for this particular method, we want to speed up. We want to speed up by the rate that's passed in. So here's the implementation of the speedup method. And then there's a slowdown method, which does the exact same thing, only instead of plus equal, it's minus equal. So this would be in a file called vehicle.cpp. You can compile this file separately. You'll have your object code, which will be called vehicle.o. You can take that file, put it on the shelf. It's done. Now you have other things. You've got auto, which will implement it. You've got a driver, which will call it and use it, and et cetera, et cetera. All these other objects in your code will all be compiled individually and separately into O files, and then they'll be linked together into an application. Now, if the driver class changes, you go and you redo the driver code, you change it, you recompile it. You don't need to change this code because this code did not change. And the more well-designed your system is, the more modular it is, the more this will be true. There will always be occasions where you make a change, and we need to make an improvement, or we need to go recompile this because of this slight improvement. But your goal is to minimize changing all these other things because this thing has changed. So this is why we put everything into a compilation unit. Now, a little quick thing about why you have an include guard. Let's say we have an automobile, which is derived from vehicle. So here's your file automobile.h, which is the interface to the automobile class. And we're including strings because we're going to use a string. We're including the vehicle.h file because we need to reference the vehicle class as our superclass. And we have our different methods, whatever else. Now the caller file says, I have got vehicles that I'm using. So I'm going to have a vehicle, which will just be some generic vehicle called V. So I'm going to include the vehicle .h file. And I also have an automobile object, which is a specific type of vehicle. I'm going to have automobile A. Now, since I have an automobile, I need to include the automobile definition. And so let's say I put that right there, to include automobile. Well, automobile is including vehicle, but vehicle has already been included. And C++ will not let you define the same thing more than once. But the include guards will look at it as, oh, this has already been included. I don't need to include it again. So automobile includes, so if you're including both automobile and vehicle, automobile is also already including vehicle. That's why you have your include guards inside your include file. If you're running Eclipse, if I'm making a new include file, it'll automatically build them for you. You just pop them right in there. All you have to do is put your code right inside. It's a good idea to do that, even if you think you won't need it, because it doesn't hurt anything. So always put your include guards in any file that's going to be included that defines interfaces, global variables, whatever else you've got going on in your system. Now, brief discussion about whether or not to use object-oriented. Object-oriented is kind of like the big thing right now. Everybody wants you to write everything in object-oriented code. There's languages out there that are only object-oriented. You cannot get away from object-oriented. My opinion is that's a mistake. So, but fortunately, C++ is not 100% object-oriented. You don't have to use object-oriented if it doesn't immediately apply to your task at hand. So the designers are free to use whatever techniques they feel is most appropriate. So what is appropriate? Well, larger programs to be divided among team members. It says, okay, Charlie, you're going to work on this. Freddie, you're going to work on this. Janice, you're going to work on that. So, okay, I'm going to work on this particular object. Another would be is something that could become larger. Well, it's small now, but we're planning on adding more features later. So we might as well start it off as being object-oriented now so we can take advantage of the object-oriented benefits. And then later on, when you have to add more features, add more objects, it's already object-oriented. You don't need to convert things over from being an old functional procedural system to a new object-oriented. It's already object-oriented, so all you need to do is add objects or improve the existing objects. Another place where it's appropriate is objects are obvious. So, we've been dealing with racehorses and with automobiles. Well, yeah, it's an object. Yeah, it's a car. It's an automobile. It goes a certain speed. It gets a certain amount of miles per gallon. And all these attributes can be put into this object. It's very obvious. And you have simulation algorithms. Is another way to tell. If you're simulating the weather, for example, you've got algorithms that simulate what the wind does, what the clouds do. It might be a good idea to make that into an object-oriented system. Now, when is it not appropriate? And this is where I really differ from some of the other languages which force you to be object-oriented. They come up with all kinds of gimmicks to take things that should not be object-oriented, and they make them into objects anyway. So we have a small program. It's only one developer. It's always going to be small. It's always going to be just the one developer. You don't necessarily need to do object-oriented. You might want to do object-oriented anyway, but you don't have to do it. Abstract functions, for example, cosine, the volume of a cylindrical solid. That's a stupid idea to make that into an object. There's nothing objectable about cosine. The volume of a cylindrical cylinder is the area of the top multiplied by the height. And it doesn't matter whether that's a water tower or your gas tank in your car. So it's applications where there's no true object can be identified or simulated. Cosine, for example. A cosine, the square root of 4 is 2, okay? You don't need object dot square root. You don't need 2 as an object. Take the square root of my object. That's, it's ridiculous. The volume of a cylindrical solid. You could have a water tower, for example, that has a circular type. The diameter is 20 feet and the height is 20 feet, and it holds a certain amount of water. So you use your volume of a cylinder to find out what the volume. But the reason why you want to make that an object, because it might not be full. So you've got a state variable. You've got something that's not abstract. You've got something. I currently have got this much water inside the water tower. I've got a pump that's adding more water to the water tower. I've got 200 customers downstream, and they all want to take a bath at the same time. So that's going to take some water out of my water tower. So you can simulate water coming in, water going out. What is the water level going to do? Now it's a little bit more complex than just saying the area of the square multiplied by the height to give you the volume. Because now you've got an actual object. So anytime you need state information, what is it doing now? What will happen when we change something? What is the flow going in or the flow going out? Then you have an object. If you don't have any of that, then it's not an object. Don't make it an object. Well, let's move on. Well, you do have the object-oriented purist that will make it an object anyway. And that's it for today's lesson on object-oriented programming in Intermediate C++. I will see you next time at educator.com.